and then I'll be popping back and forth between the other things. Oh, this is just something I wrote down for an example problem that we're going to be doing today. But what I'd like to do first is talk about how Newton might have been able to develop the law of gravitation. And need to find the pen. There it is. The story goes that Newton developed the law of gravitation while he was on it would have been his stepfather's farm at Woolsthorpe, England. When Newton graduated from college, he went to Cambridge University. And as he was finishing college, the plague struck London. That's the one that was carried by the fleas on rats. And they actually closed down Cambridge University for 2 years. And he planned on just continuing on in his studies after his bachelor's degree or whatever they called it at the time. But he had to go home. And while he was there, he supposedly would help out with the farm some, but I guess he wasn't particularly physical in liking to do work or anything, and sometimes wasn't good for other things as well. But he spent a lot of time thinking about forces and mathematics and started thinking about gravitation. And he wrote that he looked at an apple falling from a tree, and people have taken that to mean that the apple must have fallen on his head or something. Well, he never said that. And apples fall from trees all the time. If you've ever had an apple tree in your yard, when it starts getting fully loaded with fruit, sometimes they'll just fall to the ground and you'll end up with a bunch of them under the tree that you have to clean up. We used to have one in our yard in Moses Lake, or two of them actually, two trees. But he would have seen it, and he somehow got the idea that the force that pulled the apple to the ground might be the same force that pulled the moon in its orbit around the Earth. So if we've got the Earth sitting here, and there's an apple tree on the Earth, and by the way, this is not to scale. So anyway, there's an apple that can fall from the tree to the ground. And then out here, we've got the moon, although this isn't to scale. It should be a fourth the size of the Earth. But the moon is traveling in a curved orbit around the Earth. About the first thing Newton contributed to science was to figure out the formula for centripetal acceleration. And remember, that's the one that's A is equal to V squared over R. Well, at the time of Newton, they knew about how far away the moon was. They knew how long it took to orbit the Earth. And so they could figure out the V for a circular orbit. Excuse me, you're going to have to put up with that today. That's the way my COVID is manifesting itself. The speed would be 2 pi r over the orbital period. And so, whoops, let's use a capital R for that. Anyway, he could compare the acceleration of an apple falling toward the Earth with the acceleration of the moon in orbit around the Earth. And it so happens that the moon in its orbit around the Earth is about 60 times the radius of the Earth. And he started thinking, well, let's see. The apple tree is 1 Earth radius away from the center of the Earth, and when something falls from it, it falls with a certain acceleration. He looked at the acceleration of the moon, which is 60 Earth radii away from the Earth, and saw that the acceleration of the moon in its orbit, the centripetal acceleration, was about 1/3600th of the acceleration of the apple on the Earth, which is our little gravitational constant g there. And he thought that can't be an accident. between the 60 times farther away and 1/3600th, he figured that gravitational force, the force of gravity, must depend inversely on the square of the distance. And so that's where the 1 over r squared comes from. And then he reasoned that the more massive the object was, the stronger the force would be. But then there's also Newton's third law that says if the Earth exerts a force on the moon would exert an equal and opposite force on the Earth. So he reasoned it would depend on the mass of both objects. And so that's where the M1 and the M2 come from up there. And then the capital G that shows up is just a proportionality constant. So it'll have one value in the metric system. It'll have, which wasn't even invented at the time of Newton. It has another value in the English system of units, but Newton didn't worry about that much. The important part, as far as he was concerned, was this is the value of the gravitational force. So that's a way that he could have developed the thing. And just for a couple of example problems having to do with this, pull one over here. Let's see, that's not the one to start with. Okay, here's an everyday force between things. A trackball from an old computer mouse. I don't know if you've ever seen one of these things. I've got a couple of them in the classroom, but used to be, instead of a laser that would read off whatever you have your mouse sitting, there was a little ball in there that when you moved it around, it rotated on some things, and that's how it detected where your position was. But anyway, it has a mass of about 78 grams. A box of screws that's mostly empty has a mass of 31 grams, and they're separated so their centers of mass are 10 centimeters apart. What's the gravitational force of attraction between the two? Well, we can say that M1 for the mouse or the trackball that's the 78 grams. That'll be 78 times 10 to the minus third kilograms. We need to work in kilograms on this. The box of screws, we'll call that M2. It's going to be 31 times 10 to the minus third kilograms. They're separated, so their centers of mass are 10 centimeters apart. So that'll be our R. R is going to be 10.0 times 10 to the minus 2 meters. Remember, centa is 10 to the minus 2. So we've got that, and the force then is going to be capital G M1 M2 over R squared. The only thing we don't know is capital G. This is the least precisely known constant in nature. And the reason for that is it's hard to measure gravitational forces between things sitting down on the Earth when you've got the Earth's gravity, which is much greater than the attraction between those things. And so, but anyway, we'll usually just use it to 3 significant figures, and it's about 6.67 times 10 to the minus 11th. And the units are complicated on this one. Newton meter squared per kilogram squared. However, if you look at this equation, the masses here, kilograms times kilogram will be kilograms squared. And so multiplying it by G, those will divide out. And then on the bottom, if you measure the radius or the distance between things in meters, you'll have meters squared on the bottom. That'll divide out with that. And the units that are left are going to be newtons. So that's what we have. I have no idea what the gravitational constant is if you measure it in the American system. I've never done a calculation with it in anything other than the metric system. I suppose that'd be a good unit conversion problem. You could figure it out for pound feet squared per the unit of mass in the American system is slugs. So pound feet squared per slug squared. That's, I don't know, weird combo. Go ahead. I'm not going to bother with it. Anyway, so let's plug in the numbers here. So 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. And then times 78 times 10 to the minus third kilograms times 31 times 10 to the minus third kilograms, and then divided by 10.0 times 10 to the minus 2 meters, and that has to get squared. And unit-wise, kilograms, kilograms, kilograms squared divides with those. Meters squared here, divide with meters squared there. So we'll end up with newtons, but not much. And it's that minus 11 on there that keeps this thing pretty weak. The only way you have an appreciably large force with gravitation is if one of your masses is pretty large and the distance between them isn't too great. So okay, I get something about 1.6 times 10 to the minus 11th newtons. Okay, if you breathed heavily on either the trackball or the box, you'd exert a much greater force than that. So, in fact, many orders of magnitude larger from this. It's just not that large a force between small things. So let's make something a little larger, wherever that one went. Let's calculate the gravitational force between a 3.5 kilogram baby, and that'd be a baby that would weigh about 7.7 pounds, I guess, on Earth anyway, and the planet Jupiter, when Earth and Jupiter are closest together. Well, you've never studied when Earth and Jupiter are closest together, but we can look it up in your book. And in the back of your book, there's an appendix that has astronomical data. Appendix B, not A, not B. C has the Greek alphabet in it. That's nice to know. Unit conversion, numerical constants, astronomical data. Here we go. It's got the orbit radius for all the different planets. And the way I would do this thing is just to think, okay, if here's the sun, there's Earth's orbit around the sun. We'll have Jupiter's orbit around the sun. If we just take the difference between the orbital radius of Earth and the orbital radius of Jupiter, then we'll have about the distance when they're closest together. So for Jupiter, it's 7.78 times 10 to the 11th meters. For Earth, it's 1.50 times 10 to the 11th meters. So the closest approach, the R that we'll use in this case, is going to be 7.78 times 10 to the 11th meters minus 1.50 times 10 to the 11th meters, which is, let's see, minus 1, that'd be 6.28. or let's call it 6.3 because we've only got 2 sig figs here. All right. Oh, we'll also need the mass of Jupiter. And Jupiter's mass is 1.90 times 10 to the 27th kilograms. How could we possibly know that? Well, we're going to learn how next week's lab. I just forgot what it was. I think it was 1.99 times 10 to the, I know it's about 2 times 10 to the 27th kilograms. So we can figure this out. Well, let's see. Yeah, this would be a big deal in astrology because people want to know the instant of your birth and they'll want to know where Jupiter was in space and all that jazz. But we'll just see how big a force it is. The force is G mass of Jupiter, mass of the baby divided by their separation squared. So I should probably do this on another piece of paper somewhere. Running out of room here. That force will be, okay, again, the G is 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared times the mass of Jupiter, 1.99 times 10 to the 27th kilograms. Actually, I want to make sure it is 99. It might be 90. Oh, it is. It's 1.90. So that's better. And then we've got the mass of that enormous baby, 3.5 kilograms. And we divide by the distance, which was 6.3 times 10 to the 11th meters. And let's see what we get magnitude-wise. Here it is. Okay, 1.18 times 10 to the actually 1.118. So let's just call it 1.1 because we only have 2 sig figs. 10 to the minus 6th newtons. Not much. All right, so I'll write that up here. So let's look at the gravitational attraction between that baby and a terrestrial object. So let's suppose that after the baby's born at the hospital, the mother goes outside to walk to her car, and she happens to walk past a fully loaded concrete truck with a mass of 3.0 times 10 to the 4th kilograms. I looked up the weight of a fully loaded concrete truck, and that's a typical weight for one when it's got about 10 cubic yards of concrete in it. So you see those things all the time, and the baby's 4.0 meters from the center of mass of the concrete truck. Well, this is, I don't have to look anything else up. I'll have the the mass of the truck, the mass of the baby, then I just divide by the separation between the two squared. So 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared times the mass of the truck, 3.0 times 10 to the fourth kilograms. And then again, the mass of the baby, 3.5 kilograms. And I divide by the whole mess by 4.0 meters. And see how much of a difference this makes, or if it's even comparable. Let's see, 3 second E fourth. Okay, well, it's comparable, but 10 to the minus 7th newtons. So the force that Jupiter exerts on the baby it's like 11 times 10 to the minus 7th. This is 4 times 10 to the minus 7th. So they're comparable. If the mother was only stepped a little closer to the truck, like where it was only 2 meters away, this force would get 4 times bigger, and it'd actually be larger than the force that Jupiter exerts on the truck. And it'd be easy to be only 2 meters from the center of a concrete truck. Just stand next to it and you'd be there. So anyway, this isn't a force you need to worry about. It's pretty dinky. And that one's pretty dinky too. They're nothing very significant. So we have those. Okay, here's one we can just kind of reason through. The planet Saturn has about 100 times the mass of the Earth and is about 10 times farther from the sun than the Earth is. Compared to the acceleration of the Earth caused by the sun's gravitational pull, how great is the acceleration of Saturn due to the sun's gravitation? Well, let's look at and here's the idea. Is it 100 times greater, 10 times greater, the same, 1/10 is great, or 1/100th is great? Well, let's look at the force again. And in this case, it's going to be capital G times the mass of the sun times the mass of the thing, whether it's Saturn or the Earth. And then we divide by the radius, the distance between the sun and the thing. So sun thing radius squared. Okay. Well, that's the force. That force will equal the mass of the thing times its acceleration. That's what produces the acceleration. And so the acceleration ends up equaling G times the mass of the sun. The mass of the thing divided by the radius of the sun thing separation. So we have that. And it turns out that the acceleration doesn't depend on the mass of the thing. It depends on this. Well, Saturn is 10 times farther out. And so the radius of the sun Saturn is 10 times bigger than that of the Earth. But that radius gets squared and it's in the bottom. And that means when you square it, square 10 times the distance, you'll get something 100 times as big in the bottom of the fraction. And so the acceleration of Saturn due to the sun's gravitation is 1/100th as great as that of the Earth due to the sun's gravitation. So you can do a lot of reasoning just keeping in mind the fact that gravitation is an inverse square or force is what we call it. Something that depends inversely on the square of the separation between things. So a lot of that stuff works. Okay, I may switch back to that PowerPoint for a minute. And let's see. Oops, I have to get my mouse back on that thing again. So let's look at weight for a second here. And I'm hoping this is going to work. It looks like last time I had this open, I was editing some equations using that software that my license expired for. And so some of them might vanish. We'll see. But I can write them in. But for an object on the surface of the Earth, like you standing on the Earth, the gravitational force exerted by the planet is, yep, it vanished. Okay, I'll have to write it in by hand. Yeah, all right, to heck with that. We'll just do it on paper here. Okay, and I'll switch back to the visualizer again because I know that works. Okay, so weight is equal to, well, let's just call it the force that the Earth exerts on you is going to equal G times the mass of the Earth times the mass of you divided by the separation between you and the center of the Earth. Okay, well, that's about equal to the radius of the Earth. In fact, the radius of the Earth is about 6.37 times 10 to the 6th meters. Okay, roughly. If you're standing on the Earth, the center of you is about 1 meter above the surface of the Earth. And adding 1 meter to this isn't going to make much difference. In fact, this varies depending on your location on Earth. If you're standing on top of a mountain, you're farther away. If you're on the equator, the Earth actually bulges a little bit at the equator because it's spinning on its axis. And when it solidified from a molten glob, it was spinning fast enough for the equator to be bulged ever so slightly with respect. It's not a perfect sphere anyway. It's got equatorial bulges, which you get if you eat too many donuts. But anyway, it doesn't matter that extra meter you are away from it. We'll just stick the radius of the Earth squared down here. And this is your weight. Okay, crucial details here. It depends on the mass of the Earth and the mass of you, and it depends on how far away you are from the center of the Earth. So that's your weight on Earth. Well, what if you go to the moon? What will your weight be? If you go to the moon, you'd be you'd be squaring 60 times this because on the moon, you'd be 60 times farther away from the Earth, from the center of the Earth. And so it would drop to 1/3600th of the value. But on the moon, you're a whole lot closer to something else that has a lot of mass, and that's the moon. So on the moon, your weight would be that force that's exerted on you is going to be G times the mass of the moon times the mass of you divided by the radius of the moon. squared. And the part that has changed going from the Earth to the moon is this ratio right here. Okay, the mass of the moon over the radius of the moon squared. Now, it turns out that the mass of the moon is about I think it's approximately 1/85th the mass of the moon, or the mass of the Earth. So if that's all it was, you'd weigh 1/85th on the moon what you do on the Earth, except the radius of the moon is smaller. Excuse me again. And when you take into account the mass of the moon divided by the radius of the moon squared, you get something that's about 1/6 of the same ratio for the Earth. And so your weight on the moon is actually about 1/6 of what it would be on the Earth. And then the Earth is still exerting a force on you on the moon, but it's 1/3600th the value it was here. And this is going to be 1/6 the value that it was on Earth. So when you were on the surface. So this is way bigger than that 1/3600th of this. So you can ignore that when you're on the moon. And what matters when you're on the moon is the mass of the moon and the radius of the moon. Technically, your weight at any given time is the sum of the gravitational force on you from every object in the universe. But if you're standing on the surface of the Earth exerts a force that is way greater than the force from the moon or the force from the sun or the force from all the other objects in the universe. And so you can get a good measure of your weight just by considering the mass of the Earth and how far you are from the center. Now, it gets thrown off a little bit because the Earth is rotating, and we'll talk about that in a few days, the difference between true weight and apparent weight. So we can deal with that later. Okay, let's see. I think in the PowerPoint there is something more I can do. Yeah, more vanishing equations. Great. These things look not getting there. Oh, okay. There's one up there now that I think we can deal with. It's a conceptual question, and might work out okay. Okay, hopefully what you're seeing now is a question that says, at what point, I need to open the chat just in case somebody here I screw up, but it says, at what point on the diagram will the gravitational force be less than 1/4 of what it is on the Earth's surface? So I hope that's what you're seeing, and we'll work our way through here. Wow. Maybe this will work. Okay, point A is about 20 miles above the surface, and this is above about 99% of the Earth's atmosphere. This is roughly the height that, a few years ago, a guy jumped out of a balloon at this altitude, and he was wearing kind of a spacesuit and a parachute. And after a while, Felix Baumgartner was the first guy's name. And then a Google executive did it a few months later from a somewhat higher altitude, but they were both around 20 miles above the surface of the Earth. So that's that one. And then point B is about 250 miles above the surface. And that's about where the International Space Station orbits. And point C is about 350 miles above the surface and is about where the Hubble Space Telescope orbits. So the Hubble Space Telescope is still doing productive work. For the last servicing mission for the Hubble Space Telescope, which probably none of you would happen to remember, but it was kind of a big deal at the time. The pilot of the space shuttle on that mission was a graduate of the Big Bend Community College flight program. So that was kind of a cool thing. So here are the choices. A, the gravitational force at point A is less than a fourth of what it is on the Earth's surface. B, the gravitational force at point B is less than, and C, gravitational force at point C. Or D, the gravitational force at A, B, and C is less than a fourth of what it is on the Earth's surface. And E, at none of these points is the gravitational force less than a fourth of what it is on the Earth's surface. Huh. Well, think about it for a minute. And go ahead and jump to a conclusion if you want to. Now, I'm going to see if I can make my mouse pointer as pinned. I think this will work. I won't pin you down as to which one is which. But the key thing to think about is that the gravitational force depends inversely on the square of the distance between things. And if you think about right down here, approximately, being the center of the Earth, it's not that difference between going from the center of the Earth to the surface of the Earth and going from the center of the Earth to A or B or C. They're not a huge difference. In fact, B is where the International Space Station orbits. The gravitational force on an astronaut on the International Space Station is about 88% of what it is on the surface of the Earth. So they weigh 88% of what they do there. In fact, somebody could do something. They could build some kind of a great big pyramid that was as high above the surface as the orbit of the space station, and this would be a nice scam. They could put a scale on top of there, and people could ride an elevator up to that spot and stand on the scale, and it would be an instant weight loss of about 12%. And so they could extract all kinds of money from people who'd stand up there and think, oh, I weigh so much less than I did on the surface of the Earth. I've been trying to do this for years, and it's just a scam. They still have the same amount of mass that they did on the Earth's surface, so that wouldn't do it. Well, how can those guys in the space station look like they're weightless? They're enjoying something that you could enjoy anytime you wanted to, although for not for a very long time. If you stood on a chair and stepped off the chair, for the instant between when you step off the chair and you hit the floor, you'd be in the same state they are, in a state of free fall. You'd be freely accelerating toward the surface. Well, that's what the people in the space station are doing. They just happen to be going sideways so fast that they don't hit the surface. For every little bit they fall toward the surface, they travel sideways far enough so that the Earth curves away from them. And that's the trick to staying in orbit. So, okay, here's something you can do with approximately fourth grade mathematics. It's not rocket science. Rank the planets on the diagram according to your weight on each planet from heaviest to lightest. And this is something, if we did this in class, I'd pause the thing for 5 minutes and let you kind of figure it out, talk it over among the people on your table, and we'd see what would happen. In fact, if you're watching this as a recording, you could pause it here and see if you can figure it out. But I may just, well, actually, I won't. We can talk about this later and figure it out. So we'll just skip on from here and do some other mathy ones. Or do one other mathy one at least. Okay, I'll go back to the visualizer again. And this one has to do with neutron stars, is a problem out of your textbook. The one at the center of the Crab Nebula, there's a neutron star there. Neutron stars have strong magnetic fields, and they can spin rapidly on their axes. And sometime a week or so ago, I looked up the fastest spinning neutron star, and it's a thing with a mass about equal to that of the sun. But they can spin hundreds of times per second. And so you could pick up on that. If their magnetic field happens to be aimed toward the Earth, it'll show up. We can record the signal of them. And the first neutron star that was discovered, the astronomers who discovered it, actually a woman named Jocelyn Bell, was a graduate student at the time. Of course, her thesis advisor got credit for it, even though she'd done most of the work of the observations and setting up the telescope and stuff, but that's just the way it goes. But anyway, they got this electromagnetic signal that kept showing up on this radio telescope they'd built, and it was just this regularly occurring pulse. And at first they thought it was something terrestrial in origin, or maybe a satellite that was orbiting, because this was in the early days of satellite launches. And it wasn't that. And then they realized that it was coming up 4 minutes earlier every day is when it showed up. And it turns out that the rotation of the Earth with respect to the distant stars isn't 24 hours, it's 23 hours and 56 minutes. And so things that are extraterrestrial and a long ways away, like stars, would show up 4 minutes earlier every day. And this Crab Nebula happened to, although they didn't know the direction to it at first. But at first they thought, well, maybe it's some extraterrestrial intelligence sending us this thing. And they nicknamed the signal they were getting LGM1. And the LGM was a joke. It stood for Little Green Men. And then they realized that it was a rotating object, and any object that was rotating, like if the Earth spun that fast, it would fly apart. Anything that's held together just by gravity would fly apart, or even the electromagnetic force, it would fly apart. The only thing they knew of that could be was a theoretical construct called a neutron star. And a neutron star is the leftover core of a large star that collapses. If it's very large, it'll collapse to a black hole, but if it's not quite so large, it'll collapse to a neutron star. And it's basically a nucleus that has a diameter of roughly this, and it's held together by the strong nuclear force. And they are the most spherical objects in the universe because if they're not perfectly spherical, they'll have some deformations, and the forces on those things will be incredible, and everything just gets flattened out on a neutron star. So pretty amazing critters. Anyway, let's figure out if you weigh 675 newtons on Earth, what would be your weight at the surface of a neutron star that has the same mass as the sun? And by the way, the mass of the sun, need to look that up. I think it's 1.99. Yes, it is. Okay. That's the one that has the 1.99 on it. 99 times 10 to the 30th kilograms. So that would be the mass of this neutron star, but it's got a diameter of only 20 kilometers. So let's go ahead. We know that your weight on the Earth is equal to your mass, the mass of you, although this may not be you, but that's okay. The mass of you times acceleration due to gravity on Earth. So the mass of you in this case would equal the 675 newtons divided by 9.81 meters per second squared. And remember, a newton is a kilogram meter per second squared, so we'll get a mass in kilograms here. Whoops. And it's about 68.8 kilograms. Although we're only given the distance to this thing to one significant figure, so this isn't going to be terribly accurate. However, on the surface of this neutron star, the force that's acting on you due to gravitation is going to be G times the mass of the neutron star, which is the same as that of the sun, times the mass of you, divided by the radius of the neutron star squared. So we can just plug in the numbers and see what you'd weigh on this thing. 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared, times the mass of the neutron star, which is the same as that of the sun, 1.99, times 10 to the 30th kilograms, times the mass of you, 68.8 kilograms. We're going to lose all these significant figures on this thing. And then on the bottom, we're going to have 20 kilometers. So 20 times 10 to the third meters squared. So we're down to 1 sig fig when we're done with this thing. And get about two, well, let's just call it 2 times 10 to the 13th newtons. Okay, you'd be a puddle, all right? With a force like that on you, you'd just be squashed down to where you're maybe an atomic radius thick, something like that, and spread out on the perfectly smooth surface of this neutron star. Well, yeah, it doesn't matter that it might be really hot, because it wouldn't matter anyway. You'd be squashed. So that's how much you'd weigh compared to your weight on Earth of 675 newtons. So not much there. Okay, there's the bit about Newton's law of gravitation. something that was a bit puzzling, or I don't know, people wondered, how could gravity possibly exert this force over a distance? How could the Earth exert a force on the moon? And how could the sun exert a force on the Earth or the planets or anything like that? And Newton explicitly stated, I make no hypotheses about how this force might be exerted over a distance. All it is that it acts, things behave as if there is a force acting them that depends inversely on the square of the distance. And I don't know, or Newton said, I don't know how that could possibly happen. And that's the way it remained until the mid 19 teens. And at that time, Albert Einstein developed what he called his theory of general relativity. And that's his theory of gravitation. And the way it works is he said that the presence of matter warps space. And it doesn't just warp space, it warps the four-dimensional space-time continuum. And that's really the way it was stated. And that, so the presence of mass warps space, and that warped space determines how other objects move through that space. And so Einstein was well beyond that. However, Newtonian gravitation works just fine for most ordinary things. So when NASA launches a spacecraft out and they want it to go visit some planet, for instance, the Voyager spacecraft that they launched in the mid 1970s, launched them from Earth. First, they launched them out to Jupiter. At Jupiter, they calculated ahead of time where they should orient the spacecraft, so when the spacecraft went past Jupiter, it would get a gravitational slingshot effect that would send it out to Saturn. I don't remember which one was Voyager 1 and which one was Voyager 2, but one of them, when it was approaching Saturn, they calculated ahead of time using Newtonian gravitation where they would have it go so that when it was leaving Saturn, it would head out toward Uranus. And then when it got to Uranus, they calculated ahead of time using Newtonian gravitation where they would have to orient its path with respect to the planet to get it to go out to Neptune. And then after Neptune, they just flung it out of the solar system, more or less. Pluto wasn't anywhere near where it would have been useful to visit. So anyway, but that was all done with Newtonian gravitation, and they didn't have to use Einstein's general relativity for that. Einstein's relativity makes much more subtle predictions than Newtonian gravitation does, but you have to be really finicky to have anything show up there. So for the most part, we can use Newtonian gravitation for an awful lot of things, and certainly everything in your everyday lives. Although, one place where Einstein's version shows up is if you have some sort of a GPS receiver and you want to know where you are on the surface of the Earth, you get signals from the satellites that are orbiting above us, and you usually have to have about half a dozen of them be over your head, or your GPS receiver has to be getting signals from about half a dozen of them for you to determine your position very precisely. But when they do that, you have to use general relativity to correct for the signals that you get from the satellites. If you didn't, you'd be, well, the errors build up over time. Like if you were using GPS to control the position of a tractor while you're plowing a field or something like that, you might if you hadn't corrected for general relativity, you might be plowing the neighbor's field up instead of your own. And so got to be a little bit careful about that stuff. But it's built into the software on the tractors, so you don't have to worry about it. Okay, there's an introduction to gravitation. We'll be continuing on with that. Next week, the lab next week is going to be doing something with gravitation where we'll use some software that simulates Jupiter's orbit. And I'm not positive that I'll be able to teach it next week. It depends on where I am on COVID testing next week. So I'll see if I can figure out a way for you to download that software. It's open source software, and so you could use it on your own. And I'm going to experiment, and so I can just download it onto my computer here. And if I can, then I'll show you how you could do that as well. And that's what we do next week. Similarly, for the test next week, I'm going to contact the testing center and see if it would be possible for you to take it there. Or I may talk to Dory Miller and see if it might be possible for you to take it in the STEM center if it's not too noisy in there. So we'll have to see how that goes. I may be not testing positive by Sunday or Monday or something like that. And if that's the case, then I can still show up. So we'll see. Anyway, I'll talk to you later about that stuff. So I'm going to stop recording here.